introduce Jeff Seeman. Jeff no, not also, but he was an organic chemist, or is an organic chemist in Richmond University. No, Richmond University in Virginia. So got it right. And Jeff has also, since many years, published many papers in the history of chemistry. So, Jeff, the floor is yours.
I'd like to thank the organizers. Can people hear me? Small. I'd like to
No, go to the microphone.
I very much thank the organizers for the invitation. It's especially pleasing for me as an American Jew to come here and support education and the education in Israel and Israeli scientists. And thank you very much. And in fact, to thank so much hospitality, Sebastian took a few of us from Masada earlier this week, and that was very touching. During the last time, maybe I could keep this time going. During the last day and a half, frequently audience members have asked speakers, what do they mean by revolution? Was this a revolution, or were these people revolutionaries? And that's almost an unfair question, because we haven't been actually defining the term. And historically, for me personally, some of my research this last few years suggested that I was dealing with a revolution in science, a revolution in chemistry. And then I realized I didn't know what was meant by that. And so I started to read books and papers that talked about revolutions in science, and discovered that no one had actually defined the term. Different papers, different researchers used certain criteria and others used other criteria. And so what I did practically was keep track of all of the criteria that I could find that had been used by many chemists and philosophers and historians, and did essentially factor analysis, which led to a certain number of characteristics that seem to occur over and over again. So I want to tell you a little bit about that story. But why should we care? The general public is interested in progress in science and media. Big things happening in the media, so that draws people's attention to science. But as I've listed 5 different bullet points here, you can read them. As scientists ourselves, either as a young scientist or maybe even a mid-career scientist, in the development of our own plans as to what we might want to do in the future, we might wish to understand what is meant by great science, and are we doing that? Is that part of our plan development? Or in addition, we can actually start to characterize how well we're doing. And we talked about the differences, in a sense, between transfer of ideas, but I would rather call these significant breakthroughs in science versus revolutions in science. That is, small achievements that are high impact and great achievements that run through an entire community. When I think in my own work in chemistry, the work I was doing involved the Woodward-Hoffmann rules, which were discovered in the mid-1960s. A chemist at that time might have looked at his field and wondered how much is known, how much is not known. And in point of fact, organic chemistry in the 1960s did not look like that. What it looked like is this. There was a tremendous void in knowledge, in one particular area, and that was in the mechanism of what's called cyclic concerted reactions. That's a detail for most of you, it doesn't really matter, but organic chemists pretty much felt that they understood radical chemistry, carbanion chemistry, carbocation chemistry, essentially how reactions occurred 85% of the time. But there was a tremendous void in what's called today pericyclic reactions. At that time in the 1960s, not knowing that these were pericyclic reactions, they were called, somewhat in jest but quite seriously, no mechanism reactions. Every chemical reaction has a mechanism. So to call something no mechanism was not a reflection on the reaction having no mechanism, but it was a reflection on how much chemists did not understand at that time. This is a title from an important book chapter at that time. Bill Doring, who is one of the greatest physical organic chemists of the era, is the person who coined the term no mechanism, and in the very first paragraph of this paper, 1962 paper, no mechanism is the designation given half in jest, half in desperation to this lack of knowledge. So half in desperation is a contemporaneous description of how organic chemists felt in terms of their lack of knowledge on this topic. And visibly, this is what it looked like. All reactions were known except for these specific types of cyclic concerted reactions, of which there were many. So I'll give you some examples. We've heard so much different non-chemical examples. So here's some examples. The key point here, and I wish I had a pointer. Cyclobutene. The middle compounds in all three rows they're all derivatives of cyclobutene. That means a four-membered ring, cyclic butene. ENE means there's a single double bond. And going from right to left, the bonds, oh, that's wonderful. Thank you. That's great. Ah, yes. You may not see it. The bonds that are dark mean they're both above the plane of this board, and one dark is above and one dash is below. So imagine cyclobutene being a planar, and when they're both up like this, and when one's up, one's down like that. Different compounds. And on the right are their products. The delta means heat. Delta means heat. So when you heat these three different compounds, they give different compounds, okay? When the single bond here is in, that's different than when the single bond is out. So the diene looks like this, and on each end there's another substituent either going out or coming in. Got that? And that's a planar molecule that's drawn too. So you can see that when you had the cyclobutene with the two substituents up, they both give an in and an out product, in and an out. When one is up and one is down, it gives out and out. Now, it turns out that when one of these is in, it bumps with the hydrogen I haven't shown over here. So it's the less stable product. This is the more stable. So the question in this particular example is, why, when you heat something, does it give the less stable product? One would think it should give the more stable product. Another type of reaction that people couldn't understand at the time was the cyclization reaction. When you take a double bond with another double bond and react them, photochemically they form a cyclobutane. That's the compound on the far right. When you heat it, it doesn't give the cyclobutane. When you take the single double bond with a diene that is two double bonds, when you photolyze it, it doesn't cyclize to the cyclohexene, but when you heat it, it forms the cyclohexene. So it's sort of a pair of reactions that just don't make any sense. And there was no understanding as to why these reactions went or did not go as I've shown you. Okay. Up until the 1960s, organic chemists had very cleverly gathered together with about 100, 150 years, maybe 120 years of history, an accumulation of intuitive explanations for all their reactions. These were truly intuitive. So, for example, they were able to follow, this is impossible for you to understand, not to worry. But the point here is, organic chemists were able to follow the course of reactions by using what we still do. We use them still, curly arrows. We would follow for example, that's a minus reacting with an H plus. It's a way of following the trail of electron density or electrons from one part of a molecule to another. It's just a simple accounting procedure, pictorial counting procedure as to how to follow the course of a reaction. Another type of intuitive analysis was called steric effects, which we use today too. That's basically saying two parts of a molecule cannot be in the same region because they overlap and they would bump, like two cars coming together. Bump, you have a collision, that would be a high energy reaction. So organic chemists knew how to use steric reactions. For example, this nitrogen is typically very reactive, but if you put very, very large groups on each side of it, then a reactant cannot get into that nitrogen. And in fact, the only way with regard to methyl iodide and methylation, we were talking about methylations earlier on, is a simple methylation reaction. The only way to do that is to heat it at very, very high pressure. High pressure forces the molecules together. So that's steric effects. Electronic effects were another type of intuitive reaction. For example, if the kind of reaction, if it required, for example, the formation of a charged molecule, if it was done in water, which solvated charges, that reaction would go quicker than if it was done in, say, hexane, which was electronically neutral. So another hand-waving kind of methodology. And the books of that era, some of which were my undergraduate texts of the 60s, they used these intuitive methods, some of which were intuitive quantitative, but they used these methods to explain all of organic chemistry, except for the no mechanism reactions. And I just listed other types of these heuristic intuitive explanations. In 1965 through 1973, Woodward and Hoffman published a series of articles which they explained the mechanism of no mechanism reactions. And their mechanism, their explanation was based on quantum chemistry. And this was the first time quantum chemistry was called upon to explain organic reactions. Even though quantum chemistry had been, of course, as you know, much studied for decades before that. I want to emphasize, there was no solution to this no mechanism problem outside of quantum chemistry. Roald Hoffman received the 1981 Nobel Prize for this work in conjunction with the Japanese chemist Kenichi Fukui, who had developed frontier molecular orbital theory in the 1950s. Woodward would have received, the Woodward-Hoffman rules, Woodward certainly would have received his second Nobel Prize. His first was in 1960, his only was 1965, but he died in 1979, 2 years too soon. So he would have been one of the rare double Nobel laureates. Oh, there's Woodward. Now, I want to do what I shouldn't do, but I think it will be fun if I can succeed here. I want to describe to you why quantum chemistry was absolutely necessary to solve this particular type of reaction mechanism, but in fact it's now generally used throughout of all organic chemistry. The intuitive methods we use all the time as well, but the quantum chemical methods have essentially replaced them in terms of rigor and validity. So why was quantum chemistry necessary? So I'm going to give you a little quick discussion of molecular orbital theory. Very, very quick. And for the theoretical computational chemists, please bear with me, okay? So, if you have two hydrogen atoms and one form hydrogen molecule, which is H2, each hydrogen atom has one electron each. And you bring them together, and with luck, those two electrons become shared and forms a chemical bond. So, on the far, here on the left is these are energy levels that are quantized for a hydrogen atom and a hydrogen atom. When the two come together, they not only form a more stable bonding level, but they also form a much less stable, what we call anti-bonding level. When you start with two levels, you must end up with two levels. So this is an addition and a subtraction. The addition gives you bonding, and hydrogen molecule is stable. That's why this level is lower than these two levels. And each one had one electron, so they come together in the electron pair, and there's no electrons on the top. So it's an addition and a subtraction. Let's take two hypothetical methylenes. Oh boy, I should have drawn the structure. I'm now taking, this is a carbon with two hydrogens. I'm sorry, I didn't think of drawing the structure. So it's a carbon with two hydrogens coming together with a carbon and two hydrogens, and they're going to form an ethylene. That's ethene, it's CH2, double bond CH2. So these two, when you add together, they form a double bond with a new bond. There's the double bond, the bond between the pair. And then when they subtract, it's this minus that gives the anti-bonding at high level. So the two come together, a new molecular orbital is formed, it's fully paired, and it's more stable. Okay? Now here's the hard one. Bear with me. Oh my. I'm now going to take two ethylenes, and I've left out all the hydrogens. So it's an olefin here, and they come together, as a positive, and you subtract one from the other, and they form a negative like that. So here's the two coming together in a positive sense, more stable, and the other in a negative sense, less stable. And then when you take the other set of pairs, you get the same kind of addition and subtraction. But we don't need to worry about the top two lines. What's of interest here is that this butadiene, this two double bonds, there are going to be two electrons here, two go here, two go here. So these are filled, and the upper ones are unfilled. Notice here, why is this the most stable? Because there's a bonding between the first and second and third and fourth. So this is the most stable because there's bonding between all of the carbons. The next highest has to be less stable, and that's because there's bonding only between 1 and 2 and 3 and 4. And then, of course, as you can see here, there's even less bonding. But we're not worried about those two. Okay. Now I want to go back to the cyclobutene reaction. But if I can share this with you, if I'm successful, this will be worth coming to Israel, really. Okay. here's the deal. We have this 1,3-butadiene, and we're going to close it. It's going to form a cyclobutene one way or another. Now imagine, I don't have enough hands, but I have to say it this way. If you want a bond to form between the top two carbons to form the cyclobutene, the dark has to turn in a direction which bonds with the other. So they both have to come in. One is clockwise and one is counterclockwise. Okay? That's the top. If you want to have a bonding between the dark and the dark, remember dark to dark is bonding, then you have to actually go opposite. One is going, at least from my side, this is going clockwise, and they're both going clockwise. Is that, you see that? To get the dark, this is all in a plane, to get the dark bonding to the bottom dark, this can rotate in, and this has to rotate out so that this bottom comes up. The distinction is goes back to here. The butadiene is plus, plus, minus, minus. It's only one of those two. It's plus, plus, minus, minus. So that when you heat that one, this is the only direction it can go. It can't go the other direction. It's forced to go in this direction, which is called conrotatory. That's just a phrase. Meaning that while there are two seemingly equal ways of bringing bonding into bear, only one of those two is energetically acceptable. If you go the other direction, you get antibonding. And the only reason that there's a bias there is that when you form a bond, you get a bonding and an antibonding bond, which has a addition and a subtraction. And because there are 4 electrons here, we're only paying attention to the top, least stable, most reactive double bonds, and that tells you you have to go top to bottom. So without quantum chemistry, you would never get to a distinction here, because the old way of thinking is it's always plus, 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 plus. Okay. So, of course, quite outside this lecture, there are just a whole host of now quantum chemical tools that theoretical chemists and computational chemists use to analyze chemistry. I have here 22 minutes used.
No, you have 10 more minutes,
10 minutes, yeah.
including discussion.
I'm watching closely. So, let's now talk about revolutions. Normal science, if we don't even think about revolutions, typically they're steps. And I've just arbitrarily drawn these steps at the same height. But that's irrelevant, that's just arbitrary. But they're just steps, and at a certain point you get to where we are today, or at any particular time in the history of science. I think this is useful for me when I'm thinking about what a revolution in science might be, is that there are also steps, but those steps are very special. They could be special because they are resolved. There are lots of reasons they could be special. We'll talk about the reasons they could be special. In 2003, I published a paper on philosophy of chemistry in a chemistry journal. And it asked the question, what does revolution in chemistry mean? and let's derive a definition and use that definition against 6 candidate possible revolutions. And this was last week or the week before when I put this together, but as of then, there's almost 10,000 article views for this bit of philosophy of chemistry in a chemistry journal. And I might add, Jack's Gold is one of the most important chemistry journals in the United States, in the world. So, as I hinted earlier, I went through the literature and gathered, well, I put these on 3x5 cards, and I had a pile like this, and then I did manual factor analysis, you know, and I wound up with what I thought were 13 individual components, and then I gathered those into factors, and here, and these are not mine. These come from books and publications. So let's look at some of them. So, causes and birthings. Well, individual and community-wide disappointments. A state of crisis occurs. Well, that fits with the Woodward-Hoffman stuff, because people were in despair. Okay, discontinuous character. So the next would be relationships between the old and the new. So there are discontinuous characteristics developed during the Revolutionary. So going from classical intuition to quantum chemistry is a discontinuous. Incommensurate of old and new theories. Well, that's certainly the case. Irreversible changes in chemists' visions and understandings. I want to tell you, after Woodward-Hoffman's first paper in January 1965, organic chemistry changed immediately, rapidly, irreversibly. The community went crazy. And in fact, chemists, many, stopped what they were doing and looked for, and started doing research, looking for exceptions or violations of what were called the Woodward-Hoffman rules. Irreversible community level change. Well, there we are. Well, okay. Ideational and conceptual qualities of the specific revolutions of chemistry. So here we talked about anomalies. Those were the no mechanism reactions. Irreversible, taxonomic and lexiconic. We have all sorts of new words to describe all this. For example, I told you conrotatory and disrotatory, depending on which way you move things. New research problems and programs. People started developing the most exquisite tests, meaning the most exquisite molecules, to see if their reactivity matched the predictions of these so-called Woodward-Hoffman rules. New instruments and novel aspects of their use are invented. Well, I don't think Woodward-Hoffman really did that. Well, if you consider quantum chemistry, quantum mechanics as an instrument, as a tool, we could argue that is as well. This is something we haven't discussed much, maybe not at all yesterday. The social construction and practical consequences. Revolutions in chemistry are analogous to social and cultural revolutions. What's the word? Violence. Old departments disappear, new departments appear. Imagine if you're working in one department and you're fired. That's a little violent, huh? Irreversible educational methods occur. There were new textbooks, new courses on molecular orbital theory and Woodward-Hoffman rules. Lots of new textbooks. And testimonials. Testimonials made by participants, observers, and academics who studied such revolutions. People wondered, why did it was such a simple thing. I should add, the explanation, that simple explanation that I showed you here, was known in the 1930s. Why did chemists who knew that not apply it to the no mechanism reaction? The answer is the people who knew molecular orbital theory were physical and theoretical chemists, but they didn't know any organic chemistry, and vice versa, and they weren't talking with each other. Woodward was the organic chemist, Hoffman the chemical physicist. So, for time I'm up to 28 minutes, so I don't have much time left. So, what I did, in fact, I walked through that a few minutes ago, item by item through the Woodward-Hoffmann rules, and I saw lots of positives. And then I applied that to quantum chemistry, and oh my, I saw lots of positives. And then I realized that Woodward-Hoffmann didn't initiate a revolution in chemistry, but through the eyes of an organic chemistry community, it precipitated that. And I'll describe that in just a, well, here it is. I think column D, figure D, is pretty much what the quantum chemical revolution in chemistry looks like. There was applications of quantum chemistry for spectroscopy, but those were few physical, chemical physicists in the corner. But once the Woodward-Hoffmann rules came out, boom, and of course what aided that in the 1960s, this was 1965, was computer technology, which didn't exist in the 50s, 40s, 30s. One of the other candidates I studied was what's called retrosynthetic analysis. What that is you want to make a complex molecule and you start breaking bonds to see what simpler molecule you could start with in the reverse direction. That is, you look at this and say, how could anyone make that? So you just break a few bonds to simpler molecules and think, how can I go backwards? And that led E.J. Coy to his Nobel Prize in 1990, and it's used all the time. So in the literature, you see these double-headed arrows. So someone was wanted to make the compound in top left, and did a couple of bond breaks in that one, and then did a couple of bond breaks in that one. And they said, I need to start with something like A and B and move forward. Well, I applied these 13 criteria against retrosynthetic analysis. And I came up with a number 4 positives and 3 mediums. And this qualitative estimate suggested to me that with regard to the whole of chemistry, retrosynthetic analysis wasn't that important. It was to synthetic organic chemists, but not to the whole. Okay. So, I'm almost there. This is the part I always hate. I love this one. The two, I don't know, maybe they're physical chemists or mathematicians. They're thinking, they get to this equal sign, and okay, what does this all mean? This is what I started. Arguably, revolutions in chemistry mean a lot more than actually what we've been discussing today and yesterday to our community and to the public. It only makes sense to have some type of definition by which you analyze whether something was a revolution or not, or whether it was a revolution in just a single discipline. One of the unanticipated consequences of my being here and my coming here was Sebastian and I had a few-hour discussion on Monday, and we're beginning a collaboration to take my current work to the next step, because he has some great ideas and I had some concerns that weren't clarified, and then he made some suggestions back and forth, and so we're already planning a collaboration. So for all of that, how wonderful to be here.
Okay.
Thank you very much.
Unfortunately, we ran out of time. If there is somebody who wants to have a very short question.
I used 3 minutes, actually.
I have something to say, because what you used as a definition is mainly the characteristics that Kuhn gave in his 62 book. And you criticized me yesterday for using Kuhn as a straw man, because his book is already so old. So I don't understand that discrepancy. And the other thing I don't understand, you say there is a disruption in the Woodward-Hoffmann things, and that they are dealing with atoms, they're dealing with molecules, they have the formula of ethylene molecule, that is all what was there before, but they bring in something new, and that was great, but it is not a total disruption.
You and I can do a debate in public. And we can write a set of articles that we'll publish together.
Yes, but really, like anomalies, most revolutions don't have anomalies. They open up new fields without anomalies.
I can tell you that the world of chemistry changed irreversibly in January 1965.
Yes, but it left intact what was before. In large parts it left intact.
Actually not. We use those intuitive methods, but we now use them with little confidence. We use those because they're easier to do than calculations, but we know their limitations. Actually, they only mirror what quantum chemistry describes.
The
So,
ethylene molecule
look,
is not an intuition.
I can tell
it is
you,
measured.
I can tell you as a practicing chemist, I have 150 publications in chemical research, and 150 in history of chemistry, okay, something like that. And I can tell you that chemistry changed irreversibly in 1965, and it's not just my opinion.
Yeah, part of chemistry changed, I agree with it.
So
But other parts did not change, so, but okay. According to Kuhn, everything has to change.
okay.